So again, back to our, now we have started working on linear systems. Again, your engineering problem will actually be to first formulate the problem in terms of a linear system. We're going to get to that once we actually figure out how to solve them so we can actually apply it or solve something, right? So at this first stage, we are playing with toy problems and just figuring out the mechanics of solution. This is possibly ever so slightly different from what you've done in your linear algebra class. If you haven't learned it, or if you forgot what you learned in linear algebra class, well, all the same, we're going to go through all of the motions again. So you're just going to either review it or relearn it, okay? And the reason why we're going through actual solving by hand, even though this is a numerical methods class, is that we want to see that mechanics so we can figure out how to program it, okay? We will be solving by hand toy problems that are 2 by 2, 3 by 3, somewhere on that, in that size. But in reality, I want to program it numerically so I can just go 300 by 300 or 3000 by 3000. Okay? So that is our motivation. So without further ado, let's actually get back to our Gaussian elimination is the method that we introduced last time. And I'm just going to quickly review it using the slide from last time. So basically, if I start, I'm going to use the example number 2 because it's a little larger. So I start with a system of linear equations. In this case, I have 3 unknowns, x1, x2, x3, and I have 3 equations, okay? That should be enough to actually have a unique solution. I don't really know that until I start solving and see whether these equations are actually independent of each other so that they can define a unique solution. Again, we could have a unique solution to a problem. We could have no solutions to a problem, okay, if planes in 3D don't intersect. And I could have infinite number of solutions. So an entire plane could be a solution or an entire line could be a solution. Depends on the problem itself. Having multiplicity of solutions, it's not necessarily problematic. It's actually often, in practical sense, desirable. Now, we're actually going to start, so our first step in Gaussian elimination. So Gaussian elimination has 2 steps, and I'm going to actually write them down right here. So my first step is reduce system to a upper triangular system, okay? And this is this upper triangle right here. And then the second part, and that's actually the system that we did here. I'm going to go through the steps in a moment. And then once you have that upper triangular system, then use back substitution to solve. So this may as well be in Greek, so let me translate. Actually, I don't speak Greek, I do speak Croatian. And sometimes I bet you feel like I do in the middle of the class. So if I have a system of equations, I write it in so-called augmented forms. So this is my matrix A of coefficients. Those are the coefficients that I put in a matrix. So they're all here. And then I have made vector B on the other side. So these are 3 values, corresponding values. And I call this augmented matrix just because I have to work on all of the coefficients at the same time when I'm adding and subtracting equations or using linear combinations of them. So my objective here is to arrive at the upper triangular system, which is solved here, which essentially has zeros below the main diagonal of the matrix. Okay? So how do I do that? I can, when I'm working by hand, I can just eyeball. Okay? Once we are programming a computer, we're going to have to be more systematic. But I can just eyeball things when I'm looking by hand. So if I have minus 3 in my first location here. Okay? And which equation comes in first, second, or third really doesn't matter in terms of a solution. Okay? So this first equation, so you have minus 3, the second one was 6. Then our idea in class last time was to multiply the first row, I use Roman numerals, 2 times first row plus second row, and just replace my second row with that. Okay? And that's what we did, and this gave us a 0 right here. Okay? And then we did the same for the third row, except that I just simply added first and third row. And I got, again, a 0 here where I wanted a 0. So what I'm using here is that I can take an equation and replace it by a linear combination of that equation and some other without changing the solution. So then I have these two zeros. Then I'm moving on to the second position here, position 2, 2. And I'm using that to eliminate the position below. So in this case, I can just subtract the 2. Okay? And whether you do minus 2 plus 3 or 2 minus 3 in terms of second row minus third row, it's all the same, really, in terms of ultimate solution. Just don't make an error while doing simple computation here. Okay? And then I have upper triangular system. So this system, so I've done my step 1, okay? And now I'm ready for back substitution, okay? And if you don't mind, I'm going to squeeze it all on the other side, otherwise I have to rewrite this entire system. So I'm going to give myself space right here. Okay? So what is back substitution? Where am I going to start? So the bottom line, this equation 3, or what it became, is saying actually minus 2x3 is equal to 2. Everybody sees that? Okay. So my step number 2 says minus 2x3 is equal to 2 based on the coefficients in this modified system. And my x3 is then equal to, wake up everybody. I know it's Friday. I slept only 4 hours. I'm still awake, so you can do it too. Okay? Okay. And now I plug that into my equation above. So when you plug it into equation above, you get that minus 2x2 plus 5 times, I already know x3, so I'm going to put it in, minus 1 is equal to minus 9. Everybody sees that? So basically minus 2x2 is equal to minus 9 plus 5, that's minus 4. So my x2 is equal to 2. Since I did mention that I didn't sleep enough, do check on my calculation today. Double check. Though probably as long as the numbers look okay, like nice numbers, we're good. When numbers start to going into 253 over 6, then you know we've got an issue. And then finally, I can put both of these into my first equation, and I'm going to get minus 3x1 plus 2 times 2 minus 1 times minus 1 is equal to, I'm going to squeeze it in, minus 1. So minus 3x1 is equal to 4 plus 1 is 5. On the other side, minus 5 minus 6, so my x1 is 2. Who is going to check for me that this solution is indeed a solution to this original system? What can I do? Plug in. Well, so I'm going to be a lazy because it's Friday, so I'm going to just pick one to plug it in. So let's plug it into the second equation. What is 6,1 minus 6,2 plus 7x3 equal to using these x1, x2, and x3. It is 6 times 2 minus 6 times 2, that's easy, that's a 0, plus 7 times minus 1, that's minus 7. So minus 7 is indeed equal to minus 7. So presumably, I didn't make a mistake in all others either. Okay? It's certainly fitting into one of these equations or satisfying one of them. I'm going to assume that it's satisfying all of them. Okay? Otherwise, I actually have to check all. I could also, if I'm lazy to compute, I could actually type in this as a matrix A, type in x2, x1, x2, x3 as a vector, and do matrix multiplication, and see that I indeed get this right-hand side over here. Everybody sees that? Okay. So I could do AX is equal to B. All right, so that is essentially Gaussian elimination. Now we're going to just make a couple of other problems. Or what happens when I have a couple of scenarios where this procedure might not necessarily work immediately. This is save. Open another. Oh no. I need to find an empty notes. Empty notes. This will do. Okay. So let us solve the following problem. Oh. Okay. Need to open it using Sketchbook. Works. Okay, so let's do the following. I have 2x2 plus 3x3 is equal to 6. 4x1 plus 6x2 plus 7x3 is equal to minus 6. 2x1 minus 3x2 plus 6x3 is equal to 2. So I want to solve this using Gaussian elimination. So first things first, I'm going to create that augmented matrix where I have coefficients of the linear system from the left-hand side together with the right-hand side. So what are my coefficients? 0, 2, 3.
3, 6.
Cool. And on the other side, 6 minus 6 and 2. So now I would like upper triangular system, and I'm supposed to use this position, which is called pivot position. So the position that I'm using typically to eliminate and get zeros below is 0 itself. Is there anything I can multiply this 0 and add it to the second row or third row to do anything to that second row? No. Okay, so what do I do? Switch. All right, so I do what called partial pivoting. Switch rows so that I get a non-zero in pivot position. To get non-zero in pivot position. Cool. So how about we just make it simple and switch these two? Am I changing my solution when I switch positions of equations? Am I changing solution? I'm going to take this that nobody listens to me on a Friday afternoon. No. Okay, so I can just do that. And I already have a 0 here, so yay. Nothing to do there. But I need to focus on this one. So what do you pick to do? I want to replace my third row with a linear combination of first row and third row in order to get a 0 here. 2 times what? Row 3 minus, that works. Don't be afraid, that works. Again, by hand, I can just pick numbers that kind of looks like I will have easy time doing the calculation, right? So let's just do that. Again, please monitor what I do. So 2 times 2 minus 4 is 0. It better be. 2 times minus 3 is minus 6 plus 6 is 0. This is going really well.
Are you doing
Minus 6, minus 12. See, my brain would be like, I want an easy route, except that it would become difficult. All right, 2 times 6 is 12 minus 7. I better let you compute. And then 2 times 2 is 4. Minus 6 is 10. Cool. Now I want to eliminate this using this. So my second pivot position, here I am speaking Croatian again, is 2, and I want to use it to eliminate minus 12. So what am I going to do? Row 3. That works. So we get then, I can just rewrite so this is 0 as anticipated, so 5 plus 6 times 3 is 23, somebody says, I'm going with it. And then I have 10 plus 6 times 6. Looked for a moment that the numbers wouldn't be good, but luckily, when I divide by 23, life is easy. So this is, I'm ready for back substitution. I have an upper triangular system. Again, you can kind of see a triangle here, right? Upper triangular system. So when I solve, I start from the bottom. 23x3 is equal to 46. So x3 is 2. Then what? Plus 3 times 2 is equal to 6. 2x2 plus 6 is 6, so 2x2 is a 0. And x2 is a 0. And then I have 4x1 plus 0 plus 7 times 2 is equal to minus 6. 4x1 is equal to minus 14 minus 6 minus 20. x1 is minus 5. So my solution, I'm going to write it up in green. x1, x2, x3. A pretty poor choice of color for the screen. By the way, when picking colors from the screen, this one is to be avoided for obvious reasons. It's for obvious invisibility. And that is minus 5, 0, and 2. Unless you're maybe on a black background or something like that. But I went with it anyway. Okay. Can somebody please check for me whether this is good? Pick one of the equations, throw the numbers in. Good. Now let's do the original system. Just that I haven't made a mistake on the way, right? Let's do the third one. 2 times minus 5 is minus 10 plus 0. Okay. Let's go with these ones. All right. It works. So this is so-called partial pivoting. And now we will do an example of figuring out, well, when do I have unique solutions, when do I have non-unique solutions and all that. So we're going to throw in a little wrench. We're still going to work with the model system. So how about this? The problem says find all solution possibilities based on coefficients CD for the system as follows, and it's a small one. 2x1 plus x2 is equal to C. 4x1 plus dx2 is equal to 7. And again, this is a toy problem. These numbers don't mean anything. When you're actually working on something, you will often want to just define C or D as some sort of coefficients that can actually change in your problem. And you want to investigate linear systems that are better than the others and like what this range of coefficients should be, especially if you have some choice. So it's good to be able to analyze, just like based on some more general values, what is the behavior of my linear system. So again, this is a toy problem, but the motivation is that sometimes you will actually have, I don't know, a range of viscosities you could use for a fluid, okay? And you want to kind of investigate how is your system going to behave given the viscosities or something of that sort. So let's actually look at this. So we just proceed and start solving and see what can we tell about the system solutions based on these numbers C and D. So I'm going to proceed as I would with Gaussian elimination. My system 2, 1, 4, this is just a D, C, and 7. And let me proceed with the elimination. So I want to get rid of this 4 here, and that's the only one I want to get rid of in a 2 by 2 system. So I want to make that 0, so what's a good thing to do? 2 times 1 minus 2, that works. So I'm going to go with that. So 2, 1, C remains the same. And then I have 2 times 2 minus 4 is 0. 2 times 1 is minus D is 2 minus D. And 2 times C minus 7. Okay. So for which C and D is this system going to have a unique solution that I can actually proceed, or it's going to be possible to begin with? If I were to solve this, I would say, well, 2 times D times x2 is equals to 2c minus 7, right? And if I don't know, for most C's and D's that just works, I can divide with 2 minus D and state the solution. In which cases I actually cannot do that. If these two, I will have a 0, so I will have a problem, right? So basically I have here this position and says 0 could be problematic. So this is where we're going to analyze. So if 2 minus D is equal to 0, basically D is equal to 2, then I have a system 2, 1, C, 0, 0, 2C minus 7. So if I'm going to have a solution at all, what has to be true for C? In terms of the numbers that I know, when I do 0 times x1 plus 0 times x2, I have to get a 0. So this has to be 0 to actually have a solution. So if C is different from 7 over 2, I don't have a solution. Okay, I'll have 0 is equal to something that is non-zero. So basically, if C different from 7 over 2, so 2C minus 7 different from 0, then there is no solution. Then there is no solution. Okay. So if C is equal to 7 over 2, so I'm going to call this 1A. 1B is that C is actually equal to, so let's just go under now that I'm writing it under. C equals to 7 over 2. Then my system is 2, 1, and 7 over 2. And 0, 0, 0. So this is possible, but it doesn't give me, that means that basically I have an equation that is linearly dependent on the one above it. So it doesn't provide me with any new constraint. And my solution is 2x1 plus x2 is equal to 7 over 2. So I have an entire line, infinitely many solutions. So basically, you can also look at it as a parameter. So x2 is 7, 2 minus 2x1. So for any x1, this is my x2, right? I have infinitely many combinations of solutions. So infinitely many solutions. So we have investigated all of the possibilities when d is equal to 2, so I have a 0 in the 2, 2 position. So now I can move on to the case that that is not the case. So now my second possibility is that d is not equal to 2. Then I can divide by it and I have a unique, this flicker. Check my connections. Right. So then I'm cool. I don't have a 0 in the position, that position. So I just have 2, 1, 0, and 2 minus d. And there's a c and 2c minus 7 here. This is not 0. So my x2 is 2c minus 7 divided by 2 minus d. And x1 is c minus this x2 based on this equation. And dot, 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 I can find it. It's something in terms of C and D. So I have a unique solution. So you can see how based on different choices of C and D, you can have all 3 possible situations. No solution, infinitely many solutions, and unique solution.
Wouldn't C minus x2 be divided by 2?
When D is different from 2, then I can divide by it, and I can just find a unique solution.
I just meant because like the coefficient for x1 is 2. It doesn't really matter that much.
Sure. Yes. Divided by 2. Yes. See what I mean about Friday? There we go. Okay. So now I'm going to give you a choice. Do you want the next topic to be programming this method? Or do you want to proceed with like just formulating systems of linear equations that solve engineering problems? Both. So that part is easy. So we can just go and do some examples how I formulate and how I get linear systems. Or we can actually go to programming Gaussian elimination. Yeah, sure. There's one person who has an opinion. He wants to proceed and program this. Let's do programming. All right. So I will go quickly to the So we have these 2 steps. One is so-called elimination and reduction to the upper triangular system. And one is back substitution. So let's start with back substitution. Okay? Okay. So take a piece of paper and let's see what happens here. I want to actually create, so I'm starting from a general system, and we're going to, in this toy problem, work with 3 by 3. Okay. So our first step they'll be generalizing this reduction. How do I get to an upper triangular system? So I can't just like eyeball and see which coefficients work and then solve a problem. I want computer to figure out the eyeballing, and for that matter, computer doesn't care whether it has pretty numbers, whether it has 2 times minus 2, or it has 2 over 3 times 253 divided by 6, okay? Couldn't care less. So let's just see what works in the most general case. If I have a general matrix here, okay, I want to multiply this by something and then add it to my second row or subtract it from the second row, however you want to formulate it, and get a 0. Okay? So solve that problem. I want that some coefficient, I'm going to call it C, C times A11 and subtract it from row 1. So row 1, A12 minus C times A11 has to be 0. What is C? Okay. So again, just larger for the last row. So A12 minus C times A11 has to be 0. That gives me C as? So it's obviously important that this is not 0, which is why we sometimes have to do pivoting. Okay. So now let's, on the paper, however ugly it is, let's multiply entire row 1 by this and subtract from row 2. That's what's written there. Multiply row 1 by A21 divided by A11. Just right now use the coefficients as they are and subtract from row 2. I want to program computer to do this. Okay? It's these lights that are flickering. I thought it was just my computer screen. And then, if I was doing this, did everybody get anything? Did anybody get anything?
The screen says A21 divided by A11. The board says
The first time. What do you mean?
we have in the board says A21 divided by A11, and on the whiteboard we have A12 divided by A11.
Up to 1. Good catch. Did I mention it's Friday? Am I allowed to sleep? So what did you get as that second row? So my second row is 0. A22 minus this C, A21 over A11 times A12. And then A23 minus A21 divided by A11 times A13. And then I also do the same thing with B2. Yes? C times B1. Do we see this? Well, I guess we're gonna continue. So our next step is actually just to program this one line and try to generalize it to program it for any row that I deal with. C times B1. So I'm doing the same as that with that last column as well.